Astronomy Cast, episode 269 for Monday, June 11th, 2012. Mass. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of University, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Everettsville. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
I am doing great. So once again, we're recording this episode of Astronomy Cast as a live Google Plus Hangout. You can join us every Monday at around 12 p.m. Pacific Time, 3 p.m. Eastern Time, 2 p.m. Central Time,
9 p.m. London.
9 p.m. London time. And the other cool thing that we're doing now is we're starting to figure out how the calendars work in Google Plus, so that you can actually, I will announce in my feed and in various places a future event that you can then put into your calendar so that your computer will complain to you the moment we actually start recording the live show. So if you feel like you've been missing these things just because you're distracted or whatever, we're getting to the point now where you'll actually get a live notification of when it's going to happen. So we'll work through all of the little tricks of this, but I'm hoping that we'll get to the point now where it'll all be really, really smooth, and you will never miss a live recording unless you choose to of anything that you enjoy. So that's what we're in the works right now. So let's get rolling. Did you have any other announcements, Kevin?
I think we wanted to bring up that we are starting CosmoQuest classes, our Cosmo Academy program, at the end of the month. We have Dear Astronomer from Twitter. This is Ray Sanders, and he's going to be teaching a 4-week, 8-session exclusive class for 8 people on our solar system, and I will be popping in and out and helping him with that class. I just won't be there every week. He's your lead instructor.
Yeah, Ray's a fantastic guy, right? So this is one of the feedback that we've gotten right from day one is that people have wanted to learn more information about astronomy, not just the kind of the high-level stuff that we do here on Astronomy Cast, but to actually take the equivalent of an astronomy course. And so this is going to be taught over the course of 8 weeks by Ray Sanders. He's
4 weeks, 8 classes.
4 weeks, 8 classes, by Ray Sanders. And Pamela is going to be jumping into various, some of these classes and participating as well. So this is an experiment. This is based on feedback that people have given us, and this is really following our objective to try and raise people's knowledge and understanding about astronomy, and to help then allow you to then be able to come back in and participate in some of the research projects that we're collaborating with scientists on at a higher level. So this is kind of, we're working our way into this bold new future. Now, where can people find out more about it? How can they join?
If you go to cosmoquest.org and click on Cosmo Academy, we list all of our classes there. You can sign up. We're organizing this through Everbright. We're going to be running the classes through Google Hangouts. And if you're a school teacher, we can provide you with continuing education credits for this, or I think they're called continuing professional development hours. And there will be a collection of certificates through CosmoQuest, so that by taking these entry-level classes, it will open the door for you to participate in more complicated projects and to sign up for more complicated classes in the future.
And how many slots do we have?
Just 8.
Just 8. That's it. So 200, was it 250? Is that right?
$240. So this is comparable lessons to signing up for intense yoga. It's cheaper than horseback riding. So I wanted to price it at the price that you'd spend on something that you're taking lessons for as a hobby.
Yeah, and we have a lot of instructors that are connected with us through CosmoQuest and Astronomy Cast, and over time, hopefully, we'll be able to provide more instruction. But definitely give us feedback if you like this idea, don't like it. I guess we'll let the sign-up speak for itself. So, all right, well, let's get recording then. So last week we talked about energy, and this week we're going to talk about mass. And here's the crazy thing. Mass, matter, the stuff that the universe is made of is the same thing as energy. They're connected through Einstein's famous formula, E = mc squared. But what is mass? How do we measure it? And how does it become energy and vice versa? All right, Pamela. So, and you know what? The time we're recording this, which is kind of weird because we're actually recording this in early July, although we say it's June. It's us catching up. We're on the eve of, we're at the moment of a really important announcement from the folks from CERN about the discovery of the Higgs boson.
We hope so. So what we're hearing. This is all rumors, speculation, people saying things they're probably not supposed to on the internet. But according to rumor, on the 4th of July, which is when the U.S. government, NASA, U.S. science organizations all like to make their announcements. Rumor has it that they're going to be announcing the Higgs boson has been found and has a mass roughly equivalent to the energy of 125 electron volts. And this is big news. I love it because, sorry, my recording stopped.
No. Where did it stop?
Dang, it's looking like it didn't record any of the last section.
Which section?
Actually, it's looking... Hold on, let me stop and play.
This might be where we redo all of Astronomy Cast.
Yeah, it's all of... So it started out recording, and I was watching the audio waves, and I just got an error message come up, and there is nothing. Let me make sure... Sorry, folks, it's live.
Welcome to live, folks.
Yeah, this is all rather horrifying. I'm seeing absolutely nothing in my audio patterns. Wait, no, okay, I can hear it. I just can't see it.
Okay, why don't you give it a listen, see if it worked.
Yeah.
Then if it did work, then we'll just start a new audio file, and then you can glue it together later.
Yeah, let me close this and reopen it. Sorry, folks. If you want to ask some questions while I'm reopening GarageBand, we can do that.
Sam Weirdo wants to get some updates on this. We actually, we posted it on Universe Today just today, and it's
Wired.
Everywhere. Wired, yeah, it's everywhere.
Yeah, go to Universe Today first, always.
Yeah,
right.
Yeah, always first. Hey, I see Torrin Atkinson.
Who's that?
Yeah, Torrin Atkinson, a friend of mine from Vancouver. He said that at his druthers he'd be sending us a star field on old black curtains put behind us on the live chats.
That would be awesome.
I don't know whether I want to. I kind of like seeing your various backgrounds, your offices and stuff, and seeing.
See, I kind of like your kitchen and kind of hate the turquoise room. Just
yeah, I know. Maybe I'll repaint the downstairs.
Okay, if you've repainted the turquoise room just tends to make you Oompa Loompa color.
I know. It makes me purple. So how's your audio doing?
I'm working on restarting GarageBand. And I now have a dog trapped in the room with me.
So Jesper says that when you said that you lost your recording, the stream bumped. So maybe you had a glitch on your computer.
I think
Lawn
so.
Boy, watching the sausage being made. Yes, you were watching the sausage being made. And you know, when you actually download this episode, none of this will be in there.
I know, it'll be glorious.
You know,
it'll be perfect.
Yeah, and might I recommend that you perhaps
try
Audacity
you keep saying that
in a future week. So Jake DeToro asks, is the Cosmic Quest class restricted to 8 viewers or just 8 participants? So there's no viewers.
A class.
Yeah, it's a class. There are 8 participants. There are no viewers. It is done as a hangout, but it's just you, the 8 people with Ray, going through the material, learning all the pieces. So that's it. Mary says astronomical patience for an astronomy podcast. And Beth Johnson says, I just got my son a shower curtain with planets on it. I earned so many mom points that day, all for such a little cost. I wonder how much of this we're going to keep.
So I can hear the audio, but I see no audio files.
You know what? Let's just start again. Let's just redo it. Let's forget it. We're just going to redo the show. And
I will make you happy by opening up Audacity.
Well, but that doesn't make me happy. Now you're starting a brand new piece of software that you've never used before.
No, I've used Audacity. I just hate Audacity.
Oh, okay, all right.
Of course, this computer may not have it. Okay, I lied. Audacity is on all my laptops. It's just not on here. Okay, starting a new file in GarageBand.
Jake, so no recordings after the fact. No, it'll all be live, and then it'll be a regular hangout, which aren't recorded. How often do the CosmoQuest classes tend to fill up? They don't.
This is our first one.
Before, so we're about to find out.
So sign up quickly. There's only 8 spots.
That's right. People said, "Oh, it'd be really cool. I'd love if I could take astronomy classes with you guys." Well, now you can. We'll find out whether people want to take astronomy classes.
And in the future, I will be teaching advanced courses. I just can't do everything, so we're starting off introducing you, and I know Emily Lactawala is going to be teaching courses in the future. And so we're working on building up a group of internet-savvy, good communicators, teaching a whole suite of different classes.
Yeah, I mean, our goal, our long-term goal here really is that we want to be able to make it so that we can build a larger and larger group of people who can assist with the various research projects that we're working on through CosmoQuest. So, if you've got a telescope and you've got, you can do spectroscopy, or you can do, that you don't need to go the PhD route to even just participate in.
We'll help.
Yeah, we'll help raise your level of experience and then really kind of bridge that gap between the researchers and the general public that are enthusiastic about participating. Honestly, we have no idea how this is going to work out, but we just need to try things. So that's.
But if things work, I'll definitely be teaching a course on CCD photometry and variable star observing and things along those lines. Yeah,
and then just the kinds of specific tasks that people can get involved in. But we're probably going to start with basic classes like our Astronomy 101, that's sort of a prerequisite, that then you can go into those other things and understand what's going on. So that's the goal, the long-term goal. Right now we just have to start with those basics.
But we're about to explain this again as we start over Astronomy Cast.
I know.
Okay, I seem to be ready now.
Yeah?
I'm going to dare to press record.
Okay, I'm pressing record. I pressed record. It worked just fine.
I pressed record. I see audio thingies doing thingies.
Do you? Okay, keep that somewhere where you can watch it.
Yeah, it's right there.
All right. Oh, here we go then. Round 2. This has happened more times than you ever knew. All right. Astronomy Cast, episode 269 for Monday, June 11th, 2012. Mass. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hi, Pamela. How you doing?
I'm doing well. How are you doing, Fraser?
Doing great. So once again, I want to remind people that we are recording this episode of Astronomy Cast as a live Google Plus Hangout on Air. So if you want to watch us live, you just have to come to either the Astronomy Cast page or Pamela's page or my page on Mondays at noon Pacific, 3 Eastern, 2 Central, 9 London time, and you can watch us record live, ask us questions, and just sort of watch us goof up recording the episodes. But the other thing we want to announce this week that's really cool is that we now have a new, the CosmoQuest Academy, where we're going to be teaching you astronomy directly. So can you explain this, Pamela?
So the first course that we're offering, we're going to have Dear Astronomer Ray Sanders teaching a course on Solar System 101. It's 8 one-hour classes taught across 4 weeks. And our goal is to give you that Astro 101 section on planets, teaching you about how the solar system formed, the different types of planets, how extrasolar planets are formed, and the diversity of worlds that occupy our galaxy. If this works, we're going to continue to build more and more classes in the future. We are offering all teachers professional development hours for these courses, and we also have a certificate program so that by taking this entry-level course, over time you'll gain access to more advanced projects and to more advanced courses. In the future, I'll probably be teaching something on CCD data reduction and photometry so that you can get engaged in things like variable star observing.
Yeah, and Ray Sanders is a great guy. He runs the website Dear Astronomer. He's constantly been educating people, and we've worked with him in the past, and so it's going to be a really great fit to have him there teaching people. And I know, Pamela, you're going to be dropping into some of these courses as well. So so this is a way to kind of take your astronomy knowledge to the next level without going and plunking down all that money for a PhD in astrophysics.
And we're restricting enrollment in the course to just 8 students. And we're doing this for a couple of different reasons. One is so that both Ray and I can fit into the Hangout with you. But the other is we wanted to have as close to one-on-one instruction as we can. It does have a price. It's $240. But that price was set based on how much would it cost to sign up for yoga? How much would it cost to take advanced karate lessons? How much do I spend on horseback riding lessons?
Yeah.
And so we wanted this to be consistent with how much money you'd pay to advance a hobby interest.
That's cool. So people can find out more. They go to cosmoquest.org/Cosmo Academy. Is that right?
I believe so. There's a link. Just go to cosmoquest.org.
Go to CosmoQuest, yeah. You'll be able
click
to find
on
out
Cosmo
more.
Academy.
All right. Well, let's get rolling with this episode now. So last week we talked about energy, and this week we'll talk about mass. And here's the crazy thing. Mass, matter, the stuff that the universe is made of is the same thing as energy. They're connected through Einstein's famous formula, E=mc². But what is mass? How do we measure it? And how does it become energy and vice versa? And so the really cool thing about this actually is that, I mean, although we said the date was June 11th, we're actually recording this in early July, moments before a rumored big announcement from CERN about the discovery of the Higgs boson. So what's going on?
So this is pure conjecture. People are saying, Fermilab folks are gossiping that on the 4th of July, one of the American favorite dates to announce scientific things and to land things on other planets, rumor has it that on the 4th of July, they're going to announce that the Higgs boson has been found and that it has a mass that is equivalent to the energy of 125 electron volts. And what's kind of awesome to me about this is completely consistent with the Standard Model, which is a experimentally based model that has no underlying, it has to be this because explanation. And I just love it when physics refuses to give in to the crazy radical ideas out there. And there's a ton of people who are horribly upset with the projected mass of the Higgs boson because they wanted it to be weird. Because if it was weird, it might have confirmed the supersymmetry theory, it might have confirmed many of the other here's physics, let's build particles on top of physics, versus instead, here's particles, let's build the physics on what we observe. And the universe currently is saying, I simply want to be observed, I'm not going to reveal my lower level truths, not yet.
Right. So then this is fantastic, and obviously we're going to report this. And I think one of the things that people have been asking us right from the beginning of the show is they want us to do an episode on what are the big discoveries that have changed since we started recording Astronomy Cast. And we're always like really excited to do that, and then we sit down and we pull out a checklist, and then we just kind of go, nope, not really, not much has changed. This has changed. That 5 years ago when we first started doing Astronomy Cast, the Higgs boson was a completely theorized particle. There was no way that the particle accelerators at the time could get to the bottom of this. It is now, with almost, 6 sigma level of accuracy, gotten to the point that it is a done deal. It is a slam dunk. So,
and as we creep towards our 300th episode, we are starting to finally accumulate enough of these big changes that maybe for 300 we can do one of these episodes.
For 300, yeah. But I think what's great is that means that Astronomy Cast is still as relevant if you want to go back and listen to the early episodes. And this is all part of the plan. So then let's go back to mass and talk about sort of, one of the things, there's always the people who always say, oh, I weigh 42 kilograms,
Yeah.
Yes, who always want to say, oh, you mean mass, not weight.
Right.
So what is mass? When physicists consider this concept of mass, what are they talking about?
Mass is best defined as that property of your body that causes you to accelerate less effectively when a force is applied to you. So if you have a little tiny mass and someone applies a big force, you go shooting off. If you have a giant mass and someone applies the exact same force, you might slightly move, because there's this equation, force equals mass times acceleration, and this ties together how everything moves and how things change the direction that they're moving. Acceleration is defined as either a change in the speed that you're going, a change in the direction you're going, or a change in both at the same time.
And so how is that different from weight?
So weight is your mass times the gravity pulling it down. So sorry, that actually came out wrong. Your weight is the mass that you have multiplied by the acceleration of gravity, which is the rate at which you would accelerate if someone decided to drop you off a cliff, which I don't recommend doing. So your weight is your force on the chair, it's your force on the scale. And so one way that a lot of scales work is they have the equivalent of a tightly wound spring pushing up on the top of the scale. And when you stand on it, your mass times the gravitational acceleration of the planet Earth creates a force back down on that spring. And by measuring how much the spring is compressed by your weight, your gravitational force down onto the scale, this is how we get at your weight. And the actual units of weight, that's going to be newtons, not kilograms. But people use kilograms anyways.
Well, and that's the confusing part, is my scale does not measure in newtons. There is not even a setting for newtons. And so when I write it, I'll write an article and I'll say, if you weighed this on Earth, you would weigh that on Mars. And I'd say, if you weighed, 200 pounds on Earth, you would weigh, 70 pounds on Mars. And if you weighed 100 kilograms on Earth, you would weigh 30 kilograms on Mars. And people slap my wrist and go, whoa, wait, you can't do that. A kilogram is not a measure of, it's a measure of mass, not a measure of weight. And I'll go, fine. You know what? Show me on my scale where I switch it to newtons, because it does not exist. So until then, and so then I have to write these great big long explainers just to handle all the pedants. So that's what you would, but when I say that you would weigh 30 kilograms on Mars, that is completely wrong, right? The pedants are right. The scale makers are wrong.
It's quite confusing, and kilograms is a unit of mass. Newtons is a measure of force. Meters per second squared is acceleration, and your weight is actually your force on the Earth.
Right, and so what's really important then is your mass never changes no matter where you go in the universe.
Right, but your weight does.
Your weight does.
Now,
so I guess this example, I'd take that scale, go up into space, try to stand on it in weightlessness.
Now, one of the neat exceptions is, even though the planet Saturn has a much greater total mass than the Earth, it's huge. And the force of gravity, and we've talked about this in other shows, the force of gravity is proportional to how much mass an object has and how far you are from that center of mass. And because Saturn is huge and very low density, if you were roughly out at its outer cloud levels, your weight would be very similar to your weight on the surface of the planet Earth. And it's because of that relationship between mass and distance squared yielding the force.
So then what impact does mass have in the kinds of calculations? How do astronomers get at the mass of an object?
There's lots of different ways. The base description of it is you push on something and the amount that it accelerates gives you its mass. Or you collide things, and this is the conservation of momentum idea. If you collide two objects, you know their velocity ahead of time. There's a relationship between their masses and their velocities. So you can get at things by looking at collisional systems. You can get at things by looking at how they accelerate, and then gravitationally by just comparing the forces between two objects.
And so, okay, so then you would, but obviously, we can't collide things with supermassive black holes.
And this is where the gravitational part comes in.
Right, okay.
And so here, when you're trying to get the gravity of a planet with moons, you can assume the masses have point-like their masses are so small you can basically ignore them. And so you look at their orbital parameters, and based on their orbital parameters you can get the mass of the planet. So you look at how far are they from the center of the planet, you look at how fast are they orbiting the planet, and you can calculate using orbital equations the mass of the much, much larger planet that is getting orbited. You can calculate the mass of the sun by looking at how the planets orbit the sun. Trying to get at the mass of moonless planets like Venus and Mercury kind of meant we had to send spacecraft there. That was kind of annoying. But
because you needed something to be orbiting the orbiting the planet to be able to get an idea of what the amount of gravity there is there. And once you know the amount of gravity, there's the amount of mass. Right. Okay.
So we use forces there again. In this case, we're using the gravitational force between two objects to calculate based on the acceleration we see. This is the orbit, which is constantly changing velocities, and it all basically through complicated means works its way back to F equals ma.
So how does mass then change? Are there any things that can change the mass of an object?
Well, I mean, at a fundamental level, if you start decaying the atoms that are in a blob of matter, then it's going to give off radiation of some sort. Now, if it's giving off alpha particles, this is helium atoms, it's going to be radically changing in mass. If it's giving off gamma particles, which is a form of light, it's still going to be changing in mass as this energy flies away, but it's going to be changing to a much lesser degree. So through radiative decays that give off either particles or radiation, you end up with a change in the total mass of that object, but not of the entire system. So if you look at the amount of mass in the closed box, you still have the energy, you still have the matter. When you combine them together, the amount is conserved. So mass and energy combined are always going to be conserved.
Now, will the mass of an object change if it's moving? Did Einstein have anything to say about that?
That's actually one of those things that breaks people in fabulous ways.
Yeah, and I think we actually have sent a few physicists to the insane asylum with a couple of our questions for them.
One of them did retire shortly after we asked this question, but I don't think the two are totally related.
Interesting coincidence, don't you think? Yeah. So if you move things, yeah.
So the issue is, at normal velocities, this effect is so small to effectively be zero. But as you move things faster and faster, the amount of momentum that they contain increases. And you can see this as effectively, and there's people who don't like it when you say this, you can see this as effectively increasing the mass. So what you say is the mass contained in an accelerated body that has been accelerated to the point that its velocity is now some significant fraction of c, is going to be equal to its inertial mass. The amount of mass it would have that you have to apply a force to is equal to the mass it would have when it's not moving, divided over a relativistic correction term, which is the square root of 1 minus v squared over c squared. So since 1 minus v squared over c squared is going to be between 0 and 1, the fact that you're dividing the mass by something between 0 and 1 means the mass always increases. And so this means that as you go faster and faster and faster and faster, you're going to have that v over c getting smaller and smaller and smaller as v approaches c. The 1 minus v squared over c squared, rather, is going to be getting closer and closer to 0.
Math is mind-bending.
I know. So as v gets closer to c, v squared over c squared gets closer and closer to 1. 1 minus this thing that is getting closer and closer to 1 gets closer and closer to 0. When you divide your mass by something that's getting closer and closer and closer to 0, your mass is shooting up so that as you're going infinitely close to the speed of light, your mass is approaching infinity. Now, the issue with this is the amount of force that then has to be used to accelerate you to that higher velocity is increasing as well. And the amount of energy needed to change your velocity is increasing to the point that, well, our universe doesn't contain infinite energy. So you can't actually accelerate a mass to that point.
Right. So now I think that you sort of hinted at it a little bit earlier on, which is that in a closed system you have a bunch of mass, and parts of it are radiating away, and you're going to get these particles turning into radiation. But if you consider that a closed system, the total amount of the mass and the energy that's being released still balances out to be the same amount. And this is what Einstein figured out, right? Which is that energy and mass are connected together. They're really one and the same.
And this has lots of fabulous implications. This, for instance, explains why stars don't burn out quickly. Up until we'd started to really figure out nuclear fission and fusion, as we talked about a few weeks ago, people were trying to explain stars using chemical burning, and they weren't able to get significantly long lifetimes out of them because chemical burning is a very inefficient process. But if you're able to take the entire mass of an atom and convert it to energy, that's extraordinarily efficient. This is where nuclear weapons are, for better or worse, much more powerful than dynamite and plastic explosives. So he figured out that you can hold all the energy necessary to power New York City in a potato, for instance. And that was a kind of profound way to change how we view matter and energy. And it also allowed us to look at the Big Bang as something that produced a bundle of energy that froze out to become the mass that we experience today. You are frozen energy.
Now, does energy want to be mass, or does mass want to be energy?
Well, that's a chicken and the egg issue. So if you have sufficient energy in a small enough area, it will condense out to particles. And this is what they do at particle accelerators. Right. They take two particles, whether it be protons, electrons, atoms, it all depends on the type of accelerator you have. They smash them together, and when they smash them together, all of the kinetic energy in the system, all of the mass energy in the system is released in a very small volume. And all of the energy in that very small volume, and kinetic energy is 1/2 mass times velocity squared. So when they get these suckers going at relativistic speeds, that's tons of energy there. And tons was probably the wrong word to use in a show about mass. That's shed loads of energy there.
Yeah.
And all of this energy will condense out into particles. Now the thing is, when we start to look at the future death of our universe, we look at theories that project that protons might decay into energy. Now, people have been looking for proton decay for decades, and we haven't found it, and we've put limiting ages of 10 to the 33, I believe it's seconds, or years, listen, look that number up, onto, it's a vast number. We've put a vast limiting number onto how long it's going to take for protons to decay, and hasn't been seen. But if they do decay, then eventually you're going to have all these little isolated protons decaying in their little isolated place, and this energy will be spread out over a sufficient volume that the energy isn't dense enough to condense into particles. So compact energy becomes particles. Diffuse energy sort of lies around going, I'm energy, and spreading out and cooling off and getting longer and longer wavelengths.
Right, and so it's only through this process of us turning energy into particle accelerators, pushing them through particle accelerators, that we turn it back into mass.
Right, and the awesome thing about the early universe was it initially had so much energy packed so closely together that the energy had to stay pure energy until it had spread out enough to allow the particles to start to coalesce as things cooled off. And so our early universe went from this tightly bundled pure energy cooling off into matter. And someday, the matter will decay back into energy that's diffuse. So it's this fabulous cyclic system if protons decay. And again, we don't have evidence of this. It's part of a number of different theories. But the Higgs boson is saying, hey, I support the standard model, so we may not need this.
We may not need this?
Well, this is one of those things that has a lot of people really frustrated, is as they've tried to come up with theories to explain our universe, they need slightly more esoteric physics than the standard model, which basically says we have leptons, bosons. We have these set specific things, and we know that we have a boson for the electromagnetic force, a boson for the strong force, a boson for the weak force, a boson for gravity, a boson for mass, just to even things out. And we don't know why, we just do. And it makes certain predictions. It's a theory that many people declare as boring and ad hoc, and it works.
It works.
But folks trying to come up with complicated theories that have underlying first principle physics that get you to the current standard model, they wanted things a little bit more radical, and we're not finding that.
All right, and now I'm going to ask the 4-year-old question.
Okay.
Which is the tough one. We'll save it for the end. Which is, why is there mass? So, but I mean, not like why, but this is the Higgs boson. This is the whole point, right?
And it
so
goes,
what's going on?
Why don't photons have mass, for instance? And so, according to the theory, the Higgs boson is coupled to this field that permeates all of space and time. And this field is everywhere. Don't think of it as a plane. Think of it as this thing that just permeates the entire volume of cosmos. And if something has a lot of Higgs bosons associated with it, it's strongly coupled to that field. And once you get it moving through the field, the sucker keeps moving at constant velocity. That's inertia. That's the next show. But if something doesn't have that many Higgs bosons, it's really easy to get it moving. If something has a lot of Higgs bosons, it's strongly coupled. It's harder to get moving. And so the Higgs bosons, the thing that gives you mass, is an expression of how strongly coupled you are to that field. Now, that's a very, very 4-year-old way to explain it.
I got it.
Okay, cool. So the neat way to think of this is, if you have a movie star enter a crowded room full of people who are impolite and crowd the movie star, if they make the mistake of stopping, are going to get a bazillion fans around them, and getting moving is going to be really difficult. Once they're moving, they'll probably keep going at constant velocity as everyone moves to keep up. Stopping is going to be hard because you have to stop the whole crowd of people or you get knocked over. So that idea of all of these things glomming onto you that you have to get moving and get stopped to affect your velocity, that's kind of the analogy of how the Higgs works.
Right. Well, an internet celebrity can slip through a crowded room without anyone noticing. So I see what you're saying. So then, when you said like a number of Higgs bosons, so do I have a number of Higgs bosons associated with my body? Where are they? Does every atom have a Higgs boson?
Every atom has many Higgs bosons because
has many Higgs bosons.
Think about it. You have all these different particles that make up all your different atoms. And all of these things have mass. All of them are coupled in their own way to this scalar field that permeates everything. And so just like there's little photons flying back and forth between your refrigerator magnet and your refrigerator, expressing the electromagnetic force, adhering your refrigerator magnets to the refrigerator, there are Higgs bosons flying around, adhering you to the scalar field of the universe.
Whoa.
Yeah, kind of meta.
That's really cool. So, and then, is there anything then that could overturn, at this point, this discovery, do you think?
Well, if it turns out that the internet rumors are wrong and they didn't find the Higgs boson at 125 electron volts of energy, that would clearly.
I think we had talked a few months ago that we were already at 99% certainty that the Higgs boson has been discovered. Now they're at like 99.999, which is the level of precision that physicists like to be, but they're already super sure. So.
Yeah, the one thing that I personally get bothered by is gravity is supposed to have its own boson attached to it called the graviton. But the graviton doesn't have a mass, so it's not detectable. And anytime you have something that you can't prove in a laboratory, it bothers me because you have to make a belief choice. And so there's this belief choice involved in the graviton and expressing the boson for gravity. So that's a personal bother that I wish they could experimentally say the graviton is there. But now that we can say the Higgs is there, it's much easier to believe that the graviton is there. If the Higgs wasn't there, I was going to have a lot of problems grasping onto the graviton.
Right. If you've got a model that has 9 of the 10 pieces discovered, but the 10th piece is undiscoverable, there you go.
And people talked about the top quark for a long time before it was finally determined to exist in Fermi back when I was at Fermilab back when I was an undergrad.
Yeah. Cool. Well, that was great, Pamela. So next week we're gonna move to the next sort of part of this process, and we're going to talk about inertia, which is the whole other subject, very related to mass, which is related to energy. So we're going back and discovering all these core concepts. So I think that's going to be really helpful. I almost think we should have done this a lot earlier, but whatever. Cool. All right. Well, thank you very much, Pamela. It was great as always to pick your brain about mass, and we will talk to you next week.
I will see you on the other side.
Bye.
Bye-bye.